My name is Zoltán Balázs, and I work as an IT security consultant for Deloitte Hungary. And I'm also a proud member of the Goulash team. And here you can find all my contacts where you can contact me anytime about anything that is IT security related. In the following slides, I will talk about the evolution of memory corruption attack and defenses. And I will mostly focus my talk on stack-based buffer overflows. And we will go through all the magic things like stack canary, structured exception, handling exploits, DEP, ASLR, and some new advanced mitigation stuff which can protect you against these memory corruption attacks. Because this topic is so huge, I had to narrow down this topic, and I will mainly focus my talk on memory corruption exploits. So I won't talk about Java at all, and because it's totally different. And I will also focus my talk on Windows, not because I hate the others or I hate Windows or something. I just think that in the last 15 years, Windows was the main target from the memory corruption exploits point of view. And I will also focus my talk on the high-level overviews, which means that we won't go into details like assembly. And there are an awful lot of different memory corruption exploits, and like heap overflow or format string, stuff like that. We won't talk about that one as well. We will just keep straight focus on stack overflow vulnerabilities. Why you should care about exploits? You might ask. If you're a company outside of China, or you can just put your favorite enemy here, you are mainly a target for intellectual property stealing from these guys. And when your intellectual property is stolen, either via social engineering or software exploits, because all your data is exfiltrated and all your blueprints are revealed by the Chinese or some other guys, at the end you will find your product on the local Chinese market for half the price, which is bad for your business. All right, but I personally believe that most of who you are here does not fit either in the I'm in the corporate or I'm working for the Chinese government. You are just a plain user sitting at home surfing Facebook. Why you should care about the exploits? Again, you are a target, and it might be that you might be hacked through some memory corruption vulnerability, or you are just hacked by Java. In this case, all your credit card data is stolen, internet bank hacked, blah, 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 identity stolen, or just your Facebook wall is spammed with these stupid messages. This is bad for you, really. But before we go into the real details how exploits work, I have to explain how a really basic function call works on the CPU and on the stack. This is really important, so I would like to listen really carefully. So as we can see, this is this very stupid program. What it does that there is a say hello function, and this hello function gets a user input from the command line. And after this command line is received, there is a function call with this user input, and this user input is copied into the buffer and just prints out the content of the buffer. This is really, really plain. But what happens on the stack meanwhile? You know, stack is just nothing else, just a special part of a memory which has rules how it works, like you can pop or push data on it, and that's all. And when we have this function call, at the beginning, there is this so-called ESP pointer, which is the extended stack pointer, which always points to the top of your stack. And when this function call starts, there is a new memory area allocated on the top. Like this, these are sometimes too abstract. So I was thinking that maybe I can create some analogy for how this works. And I was thinking that sometimes I feel like myself when I'm looking at assembly code or doing exploits that I'm just like Alice in Wonderland, because there are some rules which you have to follow. These are very simple rules, but sometimes you don't know where to look, what to do, what happens with you. So my analogy to these function calls will be that there are two free persons in eXploitland or Wonderland. The first and most important person is the queen. She is giving instructions to the rabbit. The rabbit is plain stupid. He follows the rules. And this is what he can do, following the rules. And we also have Alice. And in this case, Alice's goal is to change what the rabbit does. But this is not an easy task, because he has to somehow exploit the rules so he can command the rabbit doing whatever he wants. So in this case, the queen basically instructs the rabbit that you should go there, which is the stack, execute all these commands I give you, and I also give you the return address, or EIP, as we mentioned, and after you finish all your tasks there, where the stack is, then you should return here to me, and I will give you the next instructions. But for your task, you also need a bottle of water from Alice. And in the next slides, I will sometimes switch between the defensive side and the offensive side. So if you can see a knight, this is the offensive side when I'm talking about exploit. And when you see a castle, this will be the defensive side. So now we are on the offensive side, the so-called stack-based buffer overflow vulnerabilities. Stack-based buffer overflow vulnerability happens when the attacker can put more data on the stack as it was basically thought by the programmer who designed the program. And this is the slide where we have left the stack. So if the user can put more data on the stack, he can overflow the buffer and overwrite more data on the stack. So at first he can overwrite the EBP we don't care about, and the attacker can also overwrite the extended instruction pointer, the return address, where the function should return after its execution has been finished. Again, if we put more data, we can overwrite more, but we don't care about this one. This is the most important stuff. And when we put a memory pointer here, which points to a memory area in our memory where there is some magic code, and then the execution flow of the program will point here, and this magic code will be executed. So talking about Alice, it looks like that Alice gave a very big bottle of water to the rabbit, and when the rabbit was told that he should split the water in the pot, and that's his only task. But in this case, the pot overflows, and the return address is just damaged. And in this case, Alice has the possibility to change the return address where the rabbit should return. And at that new return address, Alice can give commands to the rabbit to execute those. And before all of you are bored to death, here's a little quiz for you. And the first who can answer this question can win 2 bottles of Hacker beer. Yes? Yes, that's the answer. You can grab the beer after the presentation. Yes, so PackSteam was the first team who created the first Linux kernel patch to protect against stack overflows. And I really don't want to go into the details of this history, when what happens and when, but the most important thing is here that this is really old stuff. This is not new at all. And when I was talking about this magic code, which will be executed by the CPU or by the rabbit, this is a term called shellcode. And basically, this is the code what the attacker wants to execute on the victim's machine. As in Alice, these are the instructions he wants to give to the rabbit, so Alice can escape from eXploitland. And now I'm going to talk a little bit about the mitigation techniques, how an operating system can prevent these stack-based buffer overflows. But all of these mitigation techniques are usually also effective against other kind of exploits, like it can be effective against the format string or integer overflow and stuff like that, not just against stack-based buffer overflows. There is some monitoring system which detects when this pot overflows, and if it overflows, it will basically alert the bunny, the rabbit, and the bunny will stop executing anything. So Alice cannot give the new return address to the rabbit and cannot execute his instructions. Again, this is very old stuff. As always, there are many ways to bypass these protections, and the very first method is that sometimes you can replace this random cookie value both on the stack and both where the operating system stored, which was this magic cookie value. And thinking about Alice, this is very similar when Alice can basically tamper the sensor and it won't detect if the water overflows. And the next method to bypass this stack canary and cookie protection is that sometimes the stack is not protected at all because there are no string buffers, but still stack-based buffer overflow is still possible. Again, this is very similar where a situation where the rabbit goes to a place where there is no alarm system to monitor the overflow of the pot. And again, it was a very old vulnerability, but sometimes you can guess or calculate the cookie value. So when you overflow the stack, you can put that random cookie value on the stack. Because sometimes, for example, it was just a static cookie value. It was not random at all. And there are, again, other methods. I really don't want to go into these details as well. Again, we are on the offensive side, the so-called structured exception handling exploits. I'm talking about structured exception handling exploits because in reality, when you check all the tutorials and try all the stuff, the stack-based buffer overflows just work. But when you try to exploit where there is no tutorial at all, it might happen that you cannot exploit it at all because it's not possible to exploit via traditional ways. Because it might be that you cannot override the extended instruction pointer, the return address, or you cannot jump to your shellcode, or there are stack cookies which you cannot bypass, or it is just way too complicated to trigger this exploit. And this is the reason where SEH-based exploits come to the rescue. And SEH-based exploits works basically in 3 steps, and there are no question marks in it, just profit. And the first step is that in Windows process memory, there is a structure called structured exception handling. And this is just a list of exceptions, and they point to each other. And in this SEH-based exploit, basically you can, when you overflow the buffer, you can override the very first element in the exception handling chain. And because there are stack cookies nowadays always implemented, also as an exception will be triggered when you overflow the exploit. And the program execution goes to the exception handling, but because you rewrote the address where these exception handlers are in the memory, you can change it to your shellcode and you can execute your shellcode, and there is the profit. And in the case of Alice, this looks like that when the alarm system was on, it does not really instructed the rabbit to stop execution, but the rabbit was looking for some kind of disaster recovery process, what he should do in this case. And Alice has the possibility to rewrite the address where the rabbit can find this disaster recovery process. Now we are again on the defensive side. There are some mitigation techniques against these SEH-based exploits. For example, SafeSEH, which is just about that there is a limited set of valid exception handlers which the operating system will accept. And this is similar in the case of Alice when there is only a limited set of addresses where this disaster recovery manual can be found. So Alice cannot change those to address he controls. And the other mitigation technique is called SafeSEH, where the operating system performs chain validation, because if you overwrite the SEH chain with your shellcode, the SEH chain will break. And the operating system can check whether the SEH chain is broken. And this is very similar, for example, where the disaster recovery processes are basically stamped by the queen, so Alice cannot tamper with those. Our next exploit mitigation technique is called data execution prevention on Windows. And the most important thing what data execution prevention is about, that it will mark the stack as a non-executable area on the memory. And there are an awful lot of different conventions how we call this data execution prevention. Different operating systems or even processors mark it with different names. And in the case of Alice, this data execution prevention looks like that Alice was able to change the return address where the rabbit should return. But when Alice wanted to give his own handwritten commands to the rabbit noticed that these are not the instructions written by the queen. So rabbit would not execute all these commands, and he will just stop the execution, or the process will just quit. And the most secure thing is when you set the data execution prevention at always on, because as we will see it later, it will break an awful lot of different exploits, and this is what I really recommend for you. I think from this history, the most important thing is that this is again not new, but the trends are that these protections are usually first implemented in Linux, and after some time it is implemented in Windows and sometime in OS X. Now we are again on the exploit side, and we want to bypass this data execution prevention. And the very first and most important method to bypass this data execution prevention is so-called return-oriented programming. And return-oriented programming works like when we are thinking about the Alice case, that, okay, rabbit won't execute my handwritten commands, but what if I search for all the previous commands from the queen, and I cut all these commands out, put it together to do what I want, and it will be accepted, because it's not written by Alice, it's written by the queen. And in the real world, in the CPU world, what really happens that you as an attacker, you have to find memory addresses where there are some piece of code you can put together, and when you put it together, it will execute what you want. So basically, you are reusing code from the memory. Other ways to bypass this data execution prevention is that you can mark the stack as executable, which is really funny that you can do this. But when we are talking about Alice, this looks like that basically he can tell the rabbit that you should execute my commands, really, believe me, and that's all. But if you set the data execution prevention to always on, you cannot exploit this. The next method is that you can basically disable the protection for that process. And again, this attack is not working when we are talking about always on dep. Or the fourth method is that you can copy your shellcode to a new executable area. You can basically allocate new area in the memory, mark it as read-write executable, and after that, when you put all your codes there, you can execute it. And if we are talking about browsers, a very important attack is so-called the JavaScript heap spraying. Unfortunately, I don't have time to discuss this, but this is where it really fits. The next exploit mitigation technique is called ASLR, which is address space layout randomization. This is, again, a very simple thing. It's just about that every time the system reboots, the memory layout of the computer will be different, which means that all the DLLs and all the files in the memory, they will be loaded at a different memory address. And again, when we are talking about Alice, this is different. This is the same when Alice can tell the rabbit that you should instructions. And again, the very same thing, Linux, Windows, OS X. Again, there are many ways to bypass this ASLR mitigation. And the first bypass method is the so-called, you have to overwrite the just first 2 bytes of the extended instruction pointer. And this you can do because only in the high bytes on 32-bit systems, the high bytes are random, and we need that random info in order to return. So we won't change it, but we can change the low bytes basically. And this is very similar in the Alice case where we specify the return address like, okay, I really don't know where we should return, but I know that house and you should be 4 houses left to that house, and there we will meet, and I will give you my instructions there. Because the next method is about that sometimes the entropy of this random value is very low. As always, when we are talking about random, sometimes it turns out that it is not very random at all. And there are some special corner cases you need in order to exploit this case. But usually it works. For example, the very first exploit used this second method, and it was a very big thing at that time. And what is really important here that when we are talking about ASLR, ASLR is not really effective on 32-bit systems. You need 64-bit systems in order to get real prevention. And for example, if we are talking about Windows, you also need some of the newest operating systems to achieve real randomness in this ASLR protection. And again, if we are talking about this low entropy in the case of Alice, it is similar when Alice can basically give 1,000 different addresses to the rabbit, and the rabbit will go into all the 1,000 different houses, and once they will meet, so Alice can give the instructions to the rabbit. The next method, which was very common in the past, but it looks like that it won't be feasible in the future, is the so-called the ASLR is not enforced in every module. For example, if we are talking about Java 6, Java 6 used still static DLLs in the memory, and even when the ASLR has been turned on the operating system, the Java DLLs were in the very same static memory address. And it is really funny to see that there is a new flash exploit, for example, in Metasploit, and in order to exploit this flash exploit, Java 6 is needed on that operating system, which is funny because why the hell would I attack Adobe Flash if there is Java 6 there, so whatever. But luckily, Java 7 is now better because they don't use these static addresses. And in the case of Alice, it looks like that even that the street names and house names change every time in eXploitland, there are still some fixed street names and house addresses which can be used by Alice. And the last method, which is, I think, it will be the most important in the future, is the so-called address space information disclosure, which is basically that in order, we need a vulnerability for our stack-based buffer overflows. But in order to bypass this ASLR protection, we also need another vulnerability, this so-called address space information disclosure, where we basically can query the operating system that, okay, you are randomized, but please give me the address where I can find these modules. And these are usually vulnerabilities which are fixed by the operating system as well. In the case of Alice, it looks like that even everything is random, the street names and the house addresses, but Alice can still ask an inhabitant in eXploitland where he should return. And there is this great tool developed by Microsoft called Emmitt, Enhanced Mitigation something. And what Microsoft does that when they are thinking about new mitigation techniques they want to implement in their newer operating systems, they always put it first into Emmitt. So if you cannot upgrade your operating systems, you can still use Emmitt because you will get all these new protection, mitigation techniques against memory corruption errors. And this is really cool, I think, that you don't have to upgrade, you have to install it, you have to test it, definitely, you have to blacklist, whitelist something, but you will be protected. And again, Emmitt and all these protections can be bypassed, but it makes the attacker's life so harder that they won't care, they really don't want to exploit this because there are an awful lot of easier ways to get into your system. So the main thing here is that if we are in 2003, when you want to exploit a stack-based buffer overflow, it was just a piece of cake, really. Really easy. If we want to bypass ASLR and DAP and even Emmitt, nowadays it's pretty hard to exploit. You can find vulnerabilities, but it is really, really hard to write an exploit which will be executed on all those different operating system versions. And now, this is the demo time. I have chosen basic Metasploit exploit, which is not a stack-based buffer overflow, but it's in reality an integer overflow. But it doesn't really matter for us right now. And in the first scenario, I'm going to show you that I have disabled ASLR in my Windows 7 system, so which means that there will be static addresses, and I have also modified the original Metasploit exploit module that it will use just these fixed static addresses for the exploit. Weakened my Windows 7 system by installing Java 1.6 on it, because as we have discussed, it has no ASLR protection at all, so it is always loaded at a very fixed static address, so you can build your ROP chain on this static address. fourth scenario, again, ASLR is on, and again, I'm going to use the default Metasploit exploit, but it will use the fourth method, which I already told you, that this address space information disclosure, and in this case, the exploit will exploit both the integer overflow vulnerability, but before doing this, it will basically query the operating system in a way that it can calculate where this anti-DLL DLL is located at the memory. And the last scenario is about the email protection, where I'm going to turn on only one of these protections, which is a so-called heat spray pre-allocation. And as you will be able to see, the stock Metasploit exploit users. First, you should really remove Java from your browser. You don't need that, really. I promise. If you are using Windows, then you should upgrade to the latest operating systems because they have an awful lot of mitigation techniques implemented which will make all the exploit development harder. You should also use some latest browsers which have really good built-in protections against memory corruption errors like Chrome or IE. And if you can't upgrade to Windows 8, or you are on Windows 8 but still wants the latest protections, then you should really use Emmitt because it will protect you against memory corruption exploits. If you are on Windows, upgrade browser, upgrade operating system. If you are on OS X, again, upgrade browser, upgrade operating system, and all your third-party softwares. If you are a CISO, then again, I want to recommend to all of you to remove Java from all your browsers which are used for internet browsing. There are many different ways to do this. If you want questions, ask me. I have many solutions how you can achieve this goal. And again, if you are on Windows, you should really upgrade all your Windows XP systems with Internet Explorer 6. And if you can't upgrade, you should really apply Emmitt in your organization. And you can deploy it via group policy, which is really cool. And you might think that, oh, I really want to do this because it's such a lot of work. But at the end, it will turn out that because you have deployed Emmitt and it is working, you should relax on your patching policy because there will be no exploits in the wild which can basically hack you, so you have more time for testing and debugging all the new patches. So it is a one-time work and it really pays off at the end. And again, you should always install every patches. If you are a developer, how many of you are developing stuff? Great. So again, you should remove Java from your browser because you really want to develop code with a Trojan in your operating system. You should also learn some secure application development. And if you are building and compiling all your stuff, for example, with Visual Studio, these are the switches which can be used, and sometimes they are turned on by default. And if you use those switches, it will guard basically your executables from these exploit techniques with all these mitigation techniques I was talking about. And if you want to check whether your binaries has been compiled with these switchers, you can use beanscope from Microsoft, which will tell you which executable or DLL is secure and which is not. And how many of you are here from the Chinese government, espionaging and threat intelligence? Nothing? Sorry. But if you are, but you are not raising your hands, I really recommend you to develop your own backdoor client and server and don't use Poison Ivy because we can see it's a piece of shit. And how you should develop your client and server. I was already mentioning secure application development on previous slides, but until your new and your own command and control server has been developed, you should really use Emmitt so you won't get hacked by those Luxembourgian hackers. So the main lessons here that you should always use ASLR, and both in Emmitt and Windows 8 there is the so-called ForceASLR or mandatory ASLR, which is really hard sometimes to get over it and bypass it. You should always use DAP with the always-on protection. And if you want to be on the safe side, you should really deploy Emmitt from Microsoft. And I was searching for some statistics in the Metasploit that Internet Explorer 9 has been released in 2011. And how many exploits you can find in Metasploit for EN9? There are only 2 exploits, and for one of them, you need Java 6 in order to work. And how many Internet Explorer 10 exploits you can find in Metasploit? 0. You don't have exploits in Metasploit for that. And Java 7, it has been released basically at the same time as Internet Explorer 9, and we have 16 different exploits for Java in Metasploit, for Java 7. So the main thing here is that in order to develop memory corruption exploits, it is getting harder and harder, and the price for doing this is getting higher and higher from year to year. Just think about all the Pwnium stuff where you should pawn all these browsers, and the prices for that, yeah, they were really high. And thank you for your attention. This is what I wanted to tell you.